is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to wrap up the discussion of hollow conducting rectangular waveguides, and then we'll move on to cavity resonators after that. Okay, last time around we were discussing transverse electric modes. Today, I want to briefly sketch out the transverse magnetic mode. The goal here is to solve the wave equation and because we are dealing with transverse magnetic, that means the longitudinal component of the magnetic field is equal to 0. Now, of course, we are dealing with complex quantities here, and I usually like to keep the complex notation there, just I don't like to lose track of anything. And remember, the reason why we do that is because it facilitates the analysis. It's easier to deal with exponentials and with trigonometric functions. Well, if the longitudinal component of the magnetic field is 0, the electric field, the longitudinal component of the electric field is not 0. So that's what we want to solve for. And remember, our electric fields have the form of some complex amplitude times e to the ikz minus omega t. Now, this is not a constant complex amplitude. In fact, it is a function of the transverse components x and y. It's not a function of z, however, by assumption. Okay. So, can't do anything with these two derivatives. We're going to take the derivative with respect to z twice. We're looking at the ik times ik, which is minus k squared. And then also, if I take the second derivative with respect to time, again, this amplitude out front is not a function of time. So that's going to give me plus omega squared over c squared times the complex amplitude, which is a function of x and y. And I'm just dropping off the exponential there because I've already operated on it, and now it just drops out. Okay, just as before, with magnetic fields, I can introduce a separation constant and call it k to c squared. This is the cutoff wave number. This equation has identical form to that for the transverse electric modes. The big difference, though, is in the boundary conditions. In this case, the longitudinal component of the electric field vanishes on the surface. Remember last time around, we had a different boundary condition to handle the longitudinal component of the magnetic field on the surface. But in this case, e to z is equal to 0. I won't leave out all the steps, but what you will ultimately find is that your electric field has a form of some complex amplitude, generally speaking, and it's sine n pi x over a sine n pi y over b e to the ikz minus omega t. And you can figure out the transverse components of the electric field using those relations we derived in a previous lecture. You can also figure out what the magnetic field is as well, using the appropriate relations. Okay. Now your cutoff frequency and it's really cutoff angular frequency, but everybody calls it cutoff frequency, is equal to the speed of light times the square root of n pi over AD squared, quantity squared, plus n pi over v, quantity squared. And it's identical to the expression we derived for the transverse electric mode. But again, the longitudinal field that we're solving, component of the field that we're solving for, certainly has a different form from before. Okay? And also by inspection, you can see that the lowest mode in this case will not be a 1,0 or a 0,1 mode as it was before, but in fact it will be the 1,1 mode. Okay. So that is the transverse magnetic mode. It's basically just the math to work out your solution. Okay, a little while back, this is a point I want you to ponder here for a minute. We talked about current-carrying wires, and in that I mentioned that you know, when you're back in general physics class, you don't worry about the field theory to the wires. You know, you just basically you learn about electric fields in relation to charges and some simple configurations, and then you move over to circuits. And the connection between field theory and circuits is often not made clear. And I pointed out in one of my lectures that the reason why it isn't because the field theory can get very difficult very fast. Anyway, we went over a model that was first published in the American Journal of Physics by a physicist by the name of Field, and I have that paper and others listed on the BocaPhysics website, as well as his one of his books. So anyway, the upshot of that was that you want to think of the wires as acting as railroads for the fields. It's the fields that are important, and that surface charge density appears on those wires, and the surface charge serves roles, among other things, to keep the current contained. Now, here you can consider the problems that we've been working through. We haven't even mentioned, really, of surface charge or surface currents. We made use of the two boundary conditions that the normal component of the magnetic field has to vanish at the surface, and also that the tangential component of the electric field has to vanish at the surface. But you get two other boundary conditions, and the one about the normal component of the electric field and tangential component of the H field. So in fact, we didn't make use of those because we really couldn't use them to solve the problem. But now you know what the fields are, you can figure out what the surface charge is and what the surface currents are as well. Recently I posted online, linked to it's on the BocaPhysics website, is a set of simulations of hollow rectangular conducting waveguides and the modes that propagate in them. And I show you what the fields look like, the electric field, the magnetic field, but I also show you the surface charge distribution and also surface currents as well. So that's a useful thing to look at because I think that's glossed over oftentimes in physics classes. It's not mentioned, so sometimes if it's not mentioned, well, you think, well, gee, maybe it's not there. But there certainly is surface charge and surface currents on the inside of this waveguide. Okay, so anyway, that's one of the connections I wanted to make. So if you think about the wire serving as a railroad, well, our waveguides are serving as a railroad as well. I mean, where the field's non-zero, they're non-zero in the hollow region of the waveguide. So structure itself serves as a railroad, and it's fields inside that have a non-vanishing value, and also consequently the pointing vector is directed along the axis, and you know, you're interested in time to average pointing vector as well. Okay. So you know, you're doing circuit theory, you don't worry about all that kind of stuff because when you begin, you work with DC circuits, and Kirchhoff's loop rules hold exactly. And they also work very well for low-frequency AC circuits. Once you get up into the microwave range, however, then you run into trouble. So the reason, and that kind of brings me back to the waveguides again, because here, this is in the microwave range. Waveguides very often are of this size, 2 centimeters by 1 centimeter, roughly 2 to 1, not exactly. And the reason why that is done is to maximize the single mode bandwidth. It's done for practical reasons. Okay. And I guess one final point that I wanted to make about waveguides is we've talked about the waves propagating, but where do the waves come from? Well, as it turns out, what you want to do is you want to introduce an antenna or probe into the waveguide and have it directed, pointing in the direction of the electric field. And another way of doing that is if you introduce a loop into the waveguide, a small loop, and have that such that its normal is in the direction of the magnetic field lines. That's how you can generate these modes. Okay? And there's some other techniques as well, but I'll just mention those too. Okay, so let's finish with waveguides. There's a lot more to do, of course, if you're taking a class on it, but this is as far as we'll go in this class. Now let's move on to cavity resonators. Resonator can be thought of as a waveguide, the ends of which have been short-circuited. Now we have to consider not only boundary conditions on the x equals 0 and x equals 8 surfaces, and the y equals 0 and the y equals b surfaces, but we also have to concern ourselves with boundary conditions being satisfied on the z equals 0 and what we'll call the z equals d surfaces as well. The goal, once again, is to solve the wave equation. Wave equation. It's just the Laplacian minus 1 over c squared, second partial derivative with respect to time. And we're going to look for the z component first. Once again, it's useful to work in complex notation, as always. It's much easier to work with exponentials than it is with trigonometric functions, so we go through all the math and then at the very end take the real part to find the real solution. Okay, before I get into this, since we are interested in calculating the resonances of this system, I want you to keep in mind a problem that you talked about way back in your general physics class. And that is of an RLC circuit. If you watch one of my earlier videos where I mentioned circuits of this kind, I use script letters to denote the resistance, inductance, and capacitance. However, because there's no potential for confusion here, I'm just going to revert to the conventional notation and just write it R, L, and C. Anyway, we'll assume that we are seeking a steady-state solution to this problem. So we'll have a driving potential of the form V naught e to the I omega t, and we'll assume that our current also has a similar form. Anyway, the differential equation to be solved is the derivative of the voltage with respect to time times resistance, derivative of the current with respect to time, plus the inductance times the second derivative of the current with respect to time, plus current over C. So I make this substitution, and that'll result in a bunch of factors of I omega. We've got I omega V naught e to the I omega t on the left-hand side, and the right-hand side will have resistance times current I naught times I omega times e to the I omega t. And because we've got second derivative here, we'll have the product of I omega. That's just minus omega squared. properties, we've got the final term pertaining to the capacitance. So that is the current divided by capacitance, current I naught, e to the I omega t. Well, the exponentials all drop out. Let's just knock those right out. Also, I'm going to factor out I naught from the right-hand side. And I'll divide every term through by I omega. So the first term on the right-hand side will be simply the resistance. And we've got minus the inductance times the frequency or angular frequency over I plus 1 over I c omega. And I'll write this in a little bit different form. This factor in parentheses is called the impedance. And at a particular driving frequency, resonance frequency of the circuit, when omega is equal to 1 over square root of the inductance times capacitance, this second term will drop out. And you'll just be left with the impedance equaling the resistance of the circuit. So that is called the resonance frequency. Okay. And you have one resonance frequency for a one-mesh circuit like this. So I just want you to have this in the back of your mind as we move forward with solving this problem. Okay? Let me just leave that up on the board for just another second, and we move on. Okay, so once again, you want to revert to the good old separation of variables. All right, the Laplacian in terms of partial derivatives, second partial derivatives with respect to x, y, and z, and minus 1 over c squared. Second partial derivative with respect to time, and we'll concern ourselves first with solving the solution for the electric field, okay? And as usual, E sub z is proportional to e to the minus I omega t. What's different from before is because we assumed that we had a propagating wave propagating down the waveguide. Now we've got standing waves. So, in fact, there won't be a factor of e to the ikz. We want to write this as a function of the electric field as a product of the function of some function of x, some function of y, some function of z times e to the minus omega, I omega t. And I'll substitute that into for e sub z, and we'll divide everything through by x, y, z, e to the minus I omega t. And when I do that, let's see, I can squeeze it down here in the bottom, I guess. This will be 1 over x second derivative of the function x with respect to the variable x plus 1 over y second derivative of the function y with respect to the variable y plus 1 over z. Second derivative of the function z with respect to the variable z. And then last but not least, we're going to take the second derivative with respect to time. So it's going to give me 2 minus I omegas, minus I omega times minus I omega, is going to give us minus omega squared, but then we've got another minus sign here. So this is winds up being plus omega squared plus c squared, and that is equal to 0. As before, the only way this equation can hold is that if each of these terms is a constant. So it's convenient to call this first term minus kx squared, second term minus ky squared, and the third term minus kz squared. So again, if you can't read my handwriting, it's getting a little scrunched up at the bottom. This is minus kx squared, the second term is equal to minus ky squared, and the third term is equal to minus kz squared. I'm going to have to erase this. So we'll have a set of 3 equations to be solved. So this equation right now is equal to second derivative of the variable x with respect to x plus kx squared times the function x is equal to 0. And likewise for y and z. Oops, and that should be with respect to y. Got ahead of myself there. And also, you've seen this equation many times, not just in electromagnetism, but general physics, mechanics class, if you've taken that yet. In any case, the solution there, you guessed it, is going to be a linear combination of sine and cosine. So we'll write this as C1. I'm going to pull up the subscript x on this coefficient. This is cosine. Let's do sine first. I'll write this as sine case of x, x plus C2x cosine case of x, x. And similarly for y, that'll be C1y sine case of y, y. Plus C2y cosine case of y, y, and z, C1z sine case of z, z, plus C2, z cosine case of z, z. So that's what your solution looks like, and now we want you to apply the boundary conditions. And what do you know about the electric field? You know that its tangential component has to vanish on the surface. So therefore, at x equals 0 and x equals a, function x has to be 0, and therefore the electric field will vanish on those surfaces as well. So I say if I plug in x equals 0 here, well, that's no problem. The first term just drops out. Second term, however, is going to be equal to C2x because cosine 0 is equal to 1. So therefore, I have to set C2x equal to 0, otherwise I can't satisfy this boundary condition in general. Now the second condition that x, the function x has to vanish at x equals a, well, the only way that can happen is if I put some condition on a case of x, that has to be equal to n pi over a. And in similar fashion, I can determine what the coefficients are, at least one of them, by applying the boundary conditions at y equals 0 and y equals b. Function y has to be equal to 0. Well, then, just as before, C2, so y, or I should say in similar fashion, C2y is equal to 0. And in case of y is equal to n pi over b. So far, so good. Now, what about the function z? I can't say anything about that yet because in this case, if we're looking at the electric field, the z component of the electric field, this isn't going to tell me anything about the tangential component, isn't going to help me figure out what any of these coefficients are. I'm going to go ahead and use a little bit of shortcut. I'm just going to call that f of z. And so therefore, my electric field right now I can write my electric field as a function of these three other functions. So the first term will give me sine k sub x, x. And by the way, I'm just going to leave this as k sub x for right now because I'm saving myself a little bit of room. And we'll have sine k sub y, y, and the as yet wholly undetermined function f of z. And I'll go ahead and call this, stick a complex amplitude out front. I do want to remind you though, when we were talking about waveguides, I used this notation to indicate the complex amplitude, but it wasn't constant, it was a function of x and y. And now here, this really is a constant, okay? So just a little bit of difference in how I'm using the notation right now. I can go through and do the same procedure for the functions e sub x and e sub y, the other two components of the electric field. So I'll write e sub x and call this amplitude out front, e naught x, and have a sine k sub y, y, and this time sine k sub z, z, times some function x that has the same form. Okay, it's going to be a linear combination of sine and cosine, but we as yet can't determine what that form has beyond this. And then last but not least, we've got the y component. We'll call this e sub naught y, sine k sub x, x, sine k sub z, z, and we'll stick an f of y at the end, and once again, that'll have the same form. So you see when I went through it, if you go through and write everything out, you'll see that you'll be able to determine two of these functions. Third one, we can't figure out quite yet. Make sure I got all my x's and y's where they should be. Yes, I do. Okay, so let's move on. Still have to satisfy the condition that the divergence of the electric field is equal to 0. By the way, you notice I was a little bit cavalier how I made these signs. K sub x here, K sub x down here, K sub y, K sub y, K sub z, K sub z. Now, up to now, I have offered 0 justification for using the same kz's here, same ky's, and same kx's, okay? But I was perfectly justified in doing that, and I'm going to offer that justification right now. Divergence of the electric field must vanish. So that means that when I take, let me just go ahead and write this out. Derivative of the x component with respect to x, the derivative of the y component with respect to y, and the derivative of the z component with respect to z. When I do that, the first term is going to give me So notice you have an emerging pattern here. Each of these terms has a sign, or a product of two signs in it. You got sine k is y, k is z, sine k is x and z. We have a sign basically of some x and some sine some y. This has to hold for all x, y, and z. So how can that be the case? Well, only if we're going to have a cancellation of these two factors, and these two factors. So that places a condition on what the derivatives have to be. You know, each of these functions f has this form, okay? Now, if I were to use the term sine, say that, okay, well, we'll assume that f of x has one term that's sine k sub z. You're going to wind up with a cosine, I'm going to use the right one here. You're going to wind up with a term that has a cosine of x in it, basically. And you have here a cosine of y, and here a cosine of z. There's no way that is going to cancel out. The only way is if you have f of x, one surviving term, is actually a cosine, okay? So, let's say f of x, therefore, is going to be, let's see, what are we calling this? C2s of x, cosine, case of x, fy is going to be c2y, cosine, case of y, and f of z down here is going to be c2z, cosine, case of z. Actually, let me use, let's see, we'll call this C4 and C6 here. So I don't muddle everything up. Okay, so if I take the derivative, then I'll wind up with sine case of x. This will be a sine case of y, and I'll have a sine case of z. And then this divergence condition can be satisfied. So each of these terms will then have a factor of a sine case of x, sine case of y, and sine case of z. But I'm taking the derivatives with respect to these, so that means I'm going to have an additional factor of a kx, ky, and kz. So at the end, my first term will be the form e naught x, case of x, plus e naught y, case of y, plus e naught z, case of z. And essentially what that tells you is that the electric field is going to be perpendicular to the wave vector. See, this can hold for arbitrary x, y, and z. X, y, and z do not appear in there. Okay? So let me go ahead and erase this and give myself some more working room. And basically, I'll just absorb those constant coefficients out front into these coefficients. Let me just read this off. We have e naught x, cosine case of x, sine case of y, sine case of z, e to the minus sine of omega t, e sub y, e naught y, sine case of x, cosine case of y, sine case of z, e to the minus sine of omega t. And then last but not least, we have e naught z, sine case of x, sine case of y, and cosine case of z, e to the minus I omega t. And we also have this condition that electric field is perpendicular to the wave vector. And also, because of applying the divergence condition, that was what told us that we were justified in using these same factors in the arguments of k sub x and x. Let me just write this down at the bottom, that this is equal to m pi over a, so y is equal to m pi over b, and then k sub z has the same form. We'll introduce the index L pi, and the depth of the cavity resonator is d. Okay? Next order of business is to figure out what do the magnetic field look like. And for that, we're going to make use of Faraday's law. So the curl of the electric field is equal to minus the time derivative of the magnetic field. Need to plug this in. I'm just going to go ahead and write out each of these terms separately. Okay, so I won't bother reading out, it's just the typical curl components, and of course the reason why I have a minus sign here is because just moved it from over this side to over this side. Okay, so now plugging everything in. First term, I'll go ahead and read it out, is going to be k sub y e naught z, sine k sub x x, cosine k sub y y, cosine k sub z z, and then the second term is minus k sub z, e naught y, sine k sub x x, cosine k sub y y, cosine z k sub z z, and we have a factor of e to the minus I omega t. That is equal to, take the derivative with respect to time, knowing that the magnetic field also has that factor of e to the minus I omega t, will give me I omega E naught x e to the minus I omega t. And you know what? Let me just leave that as b sub x in. Okay, second equation, we're going to write out in exactly the same kind of fashion. those are the second two terms. Let's make sure subscript can go awry here somewhere together. By the way, I'll leave it up here for a minute so you can copy it down. Write in a little bit neater form. These are x, we're going to divide both sides through by I omega. And let me read this off. Piece of x, 1 over I omega, ky, e naught z minus kz, e naught y, sine case of xx, cosine case of y, cosine case of zz, e to the minus I omega t, piece of y is minus 1 over I omega, case of x, e naught z minus case of z, e naught x, cosine case of x, x, sine case of y, cosine case of z, z, e to the minus I omega t, piece of z, 1 over I omega, case of x, e naught y, minus case of y, e naught x, cosine case of x, x, cosine case of y, y, sine case of z, z, e to the minus I omega t. And there's your complete solution. No, completely determine the electric and magnetic fields. Of course, we don't know what those three constants are yet. However, I do have this one condition that the electric field is perpendicular to the wave vector. So that means I can write one of these terms in terms of the other two. Now, the other condition that has to hold is that the divergence of the magnetic field also must be equal to 0. And you can go ahead and prove that to yourself. I won't bother with going through the math. Now, I unfortunately had to erase it a little bit ago, but basically when you substituted the derivatives and replace them by constants, this gives me a way of calculating the resonance frequency. So we'll put a little subscript LMN, and that is equal to C square root, and I'll substitute in for the x, case of x, case of y, case of z values. It's equal to m pi over a squared plus n pi over b squared plus l pi over d squared. When the driving frequency is at this frequency, that's when resonance occurs. And notice I'm just putting the index L first, so it's basically ZXY. Other people do it somewhat differently. You might write it MNL, but that's how I write it. Okay, so there are different kinds of modes that you'd encounter, and now we want to use 3 subscripts here because of L, M, and N, and we've got transverse magnetic as well. So we choose E to Z equal to 0. And in that way we have one equation that gives me one of the coefficients in terms of the other ones. So we got one undetermined coefficient here. And if you've got transverse magnetic, well, we can choose B to Z equal to 0. So that means that we've got this factor out front has to be equal to 0. And then, of course, you still have the fact that the electric field must be perpendicular to the wave vector. Okay? I should point out that the patterns that you get from making these certain kinds of assignments, it's not unique. Let's take a look at the patterns. As a matter of fact, let's look at the transverse electric mode 101. Take L equals 1, M equals 0, N equals 1. So transverse electric, we're picking E to Z equal to 0. And so that means we've got to worry about E sub Y and E sub X. Well, now I've also chosen M equal to 0. So if I choose M equal to 0, the Y component in this case is going to be 0. So not only do we have E sub Z equals 0, we have E sub Y equals to 0, and E sub X will be the only surviving component of the electric field. And I might as well just call that E naught out front, just make it a real quantity. And if I take cosine of 0, that just gives me 1. We have sine pi Y over B. And I have sine pi Z over D, and that's times e to the minus I omega t. Now, what about the magnetic field components here? Well, we already determined that's going to be 0, so Bx is equal to 0 because E naught Z is equal to 0, and well, no, I can't jump to that conclusion yet. Now, let's see which of these vanishes. The X component of the magnetic field vanishes because I'm choosing, looking at the mode TB101, that means M is equal to 0, so that's basically sine 0, that's equal to 0. B sub Y and B sub Z, however, will not vanish. B sub Y, this first term vanishes because we've assumed that we're dealing with transverse electric modes. And they have minus minus, so that's kz over I omega. And we're just calling E naught x, we're just calling that E naught. So we have cosine of 0, that's just 1 sine of pi y over b, cosine pi z over d, e to the minus I omega t. And the last term, both of these terms survive. But can make use of the fact that E naught x, case of x, plus E naught y, case of y, is equal to 0 to eliminate one of those E naught y. So E naught y is equal to minus case of x over ky, and we're calling E naught x E naught. So this is equal to, let me write it up here, minus whatever I omega, case of x squared, case of x squared over case of y, plus case of y times E naught. Again, that cosine 0 is just equal to 1. And E naught cosine pi y over b, sine pi z over d, e to the minus I omega t. And there's your solution for a transverse electric 101 mode. And everything's determined down to a factor of E naught. One important thing you want to point out, or you want to notice here, is that both of the B's have an additional factor of I in it. So what that means is that your magnetic field is out of phase with respect to the electric field. And ultimately, I do want to take the real part, so I'm going to have to erase this, give myself a little bit more room. Final solution here. You notice the electric field only has one component. That means the electric field lines are going to be straight. And magnetic field lines have two components. So there can be some kind of, not really a circle, but closed loop that lies in one plane. I noticed too that because of these are out of phase, when the electric field is maximum, in other words, say at times equal to 0, or it has an extreme, rather, times equal to pi, the magnetic fields vanish, and vice versa. So let's say that this argument together, so omega times time, is at 90 degrees, for instance, and then V and Y and VZ will be at their maximum values, and the electric field will vanish. So what happens here is that there is we're assuming we have a lossless system here, that the electric, there's a total amount of energy, and that energy alternates between being an electric energy in the electric field and the magnetic field. So it oscillates back and forth. That's another similarity between this cavity resonator problem and the LRC circuits that we looked at before. Which you got an additional resistance in there, but it's the same kind of deal. You have energy going back and forth between magnetic field energy and electric field energy. So let's go ahead and calculate the energy that's stored in this field. Well, because the energy goes back and forth, at one point, let's say time 0, the electric field will be at its maximum, magnetic field will be equal to 0. Therefore, suffices to just consider this term. knowing that the energy is going to be going back and forth between these two quantities. So this is way back in the beginning of this series. The amount of energy stored is equal to epsilon naught over 2 volume integral of the electric field squared. In this case, again, we're integrating over a rectangular parallel pipe. We're going to integrate from 0 to A, integrate from 0 to B, and we integrate from 0 to D. And you see, now I'm going to square this. This is E naught squared, sine squared pi y over b and sine squared pi z over d. We do the integral. This first integral is going to give me an a. Second integral will give me b over 2, and third integral will give me d over 2. Your answer will be ABD E naught squared over 2. Now, I could have done it the other way. I could have calculated the energy in the field when the magnetic field was at its maximum. And you'll wind up with exactly the same result. This way is a little bit shorter and only got one term to deal with here. Energy alternates back and forth between electric field energy and magnetic field energy. If we were in an engineering class, we could go a step further and actually calculate the Q of this. And the way you calculate the Q of circuits, in that case, we'd have to assume that have to think about the energy stored and about power loss and all that kind of good stuff. But anyway, I'll leave it here. It's a good exercise to go ahead and calculate the energy stored when magnetic field's at a maximum as well. Okay?